Hey, it looks like we can start. Welcome back, everyone. Well, I have all the announcements here, but let's go through them anyways. It would seem wrong not to. But before we go and do all that, any questions folks would like to start us out with today? Okay, well, it looks like the bigger part of the announcements by at least area boxes is definitely the upcoming exam. Let's go in order. We're nearly done with section 4.4. We left the last problem, well, because of a lack of time, we left the last problem for today's class. And this section 4.4 will be the last section that's on our upcoming exam 3. Section 4.6, well, this one is going to be interesting for sure. We'll still practice differentiation, but we'll be undoing it. And next class, we might be able to start section 5.1. But I did want to also mention, if you have any questions that you would like to discuss between any one of those sections, I'd be very happy to do a student-directed impromptu review day on Wednesday the 10th. It'll be at the very start of class. And so whichever questions folks would like to discuss, I'll be very happy to go over them. Even if it takes up a lot of time, I think it'd be well worth it. Then once we're done discussing review questions, however long that takes, we'll either finish section 4.6 on Wednesday's class or move on to section 5.1. Just depends on where things fall. Any questions or comments at the moment, folks, so far? Okay, aside from that, we have the same pretty much similar format for every one of our exams. We have the formula sheet that's going to be provided. Let's take a look at that while we're discussing these things. So the exam 3 formula sheet has already out of the gate a big emphasis on properties of logarithms. This will be a feature of the real exam 3. It's not going to be a heavy feature. It's not like every problem is going to use them, but there's going to be, if I recall correctly, it's been a while, at least 2 problems where you're going to need the properties of logarithms. And there's going to be one exact problem where this is the exam question. You have to expand out as part A of the problem, your expression, and then for part B, after you use the properties of logarithms, just differentiate to whatever you have. So that's going to be the first thing provided. After that, it's just the different methods that we were looking at. Third exam is all about optimization. So I've got the closed interval method for absolute maximums, minimums. The second derivative test for absolute extreme values is going to be provided, and the first derivative test as well for the same kind of purpose. So this will be your last sheet, and it'll be a real sheet that you could tear off if you choose to do so. So again, once you see these kinds of things, it's always good to kind of take inventory of what's provided as well as what's not provided. One thing that's not on here is we go to section 4 or 3.7. This is the first section on exam 3. We have to know the derivatives such as this one. Derivative of log base b of x is 1 over x natural log b. We need to know this differentiation formula as well. Derivative of natural log x becoming 1 over x. But I'd say another way to think about it is if you can go to a document like this one, or the document over here, and solve the problems that you see contained in those sections, you're on a really good track for the upcoming exam. Let me see if I can bring that stuff back. Oh, there it goes. So this came from the actual real lecture notes. I just wiped out all the formulas, so it looks like a big worksheet now. And if you want fresh problems, just like before, these come right out of the textbook. These are primarily odd problems, so you can click on show answer after you practice a problem. So that's pretty much my whole spiel for the announcements. Any questions at all, folks, before we get started? Okay, I do want to mention one additional thing before I forget. We have our upcoming quiz number 9 that's going to be due Wednesday, April 10th. And it's an important quiz. Each one of my quizzes, I try to write as honest exam questions that could show up here. So it's always good to keep track of those quizzes, put them in a nice place. In fact, if you put them all together, that could be a review sample final exam on its own. But the reason I'm mentioning all that is we'll post a new quiz down here. It'll be due the day after the exam because we make them due Wednesday. I don't want to change that. But I encourage you to try to do that quiz as soon as possible. If you solve that quiz right away, then over the weekend, my goal is to grade them as soon as possible, get them back to you before Monday, the day of the exam, so you get a little bit more feedback on section 4.4. That's where I'm going to write a quiz for. So this is the tougher section on optimization. So we'll have extra practice as a quiz. In fact, if you think of quiz number 10 as a Section 4.4, exam 3, dress rehearsal, you're on the right track. That's going to be its intention. With all that out of the way, here is another really good potential exam 3 question. I give some pretty good hints on section 4.4 because I know it's a tough section. If you run through the problems, we won't ask a question like this one. This one is meant to just be an example of how things go in these notes, but it's a good one to study. This one right here could be a potential exam 3 question because what's provided is the actual function and you just kind of launch into the process of either first derivative test or second derivative test. So that means we're definitely going to avoid these. They could be really good homework questions, but you need additional time to really think about the problem, draw a diagram, that kind of stuff. In fact, I looked at a YouTube video for drawing these things just to practice it. So think of example 2, example 4. These are the better candidates for a real exam question. And again, quiz 10 will give you another hint of about what it's going to really look like in section 4.4. It can't get too long or too technical because I know it's a timed exam. And so I'd say this is a pretty good version. Reminding ourselves of the context, here's what we left on Wednesday's class right before going to the weekend. It says the blood alcohol level, or BAC if you want it, BAL, or BAC for blood alcohol content. I think that is a real acronym. In milligrams of alcohol per liter of your blood, 10 minutes after consumption of hard liquor is given by this function right here. I'm not too certain about if the units are exactly perfect, but definitely a good problem to practice. We said here use the first derivative test because differentiating this thing twice looks like it'd be tough. This is just getting to the first derivative. We had to use the product rule to start, so that's why we color-coded it. The derivative of the function in green right here is a chain rule as well, so we analyze the process here carefully, produce that result. Then after we put this together, to really solve this kind of problem, you want to look for the greatest common factor, and it was this thing right here. And it appears right here as well, that's why it's common. And definitely factor that thing out. Factorization is going to be a big part of the exam, and even that kind of factorization is important. You should also expect to factor by trial and error, that kind of stuff that we've done in the past, but nothing too major. You wouldn't have to break out the quadratic formula. Once you get to this stage, you're still in step 1, but the goal is now to get your critical number, so you set b prime of t equal to 0 and solve. So now we're making some forward progress. The whole purpose of factoring is you can now say either the first factor is 0, or you can say the second factor is 0, which is this whole thing, 26.9 minus 2.94555. Looks like we're going for a lot of precision there. On the first equation, we've encountered this before, but it's always a good reminder. Exponential functions can never obtain 0, so this portion has no solution. Writing that small because we're not saying no solution overall. This one's a linear function in the variable t, so it absolutely would have a solution. We need to subtract 26.9 from both sides. So we have negative on both sides. Next, divide both sides by this quantity right here. And here's our standard reminder. You will absolutely need an exam or a calculator for the upcoming exam. So definitely don't forget to bring the one you're most familiar with. And now let's take the negative 26.9. I mean, it's all positive, but this is probably how you would put it into a calculator with a negative sign, potentially. A 26.9. We're dividing by this quantity, negative 2.94555. And here's our result. For this critical number, this is going to be potentially in our conclusion. So this is not a bad one to round now to a more reasonable level of precision. We'll go for 2 decimal places. 9.13 milligrams per liter. I don't know if that's a lot, but that's where we fell on. This could be a lethal amount of alcohol, but everyone's different. Everyone's liver functions different. So now that we got to this stage, here's where an exam question gets really extra tricky. It feels like this is a natural stopping point, but it's not. If we decide we're using the first derivative test, we have to show all steps of that test. That's going to be a reminder on the real exam. We'll say to show all steps of your chosen test. There'll be another reminder on the quiz. And so here's step 2. Show all steps. We chose first derivative test, so I'll say here, first derivative test. Now, if we chose the second derivative test, showing all steps would just be differentiate this again, show that this thing is always negative, and then you would have found a maximum. But for the first derivative test, we do this instead. We take a look at the variable in question. It is time after consumption of hard liquor. So naturally, our domain starts right at 0. At time 0, that's the instant right before the shot hit your system. So we'll say, this is the axis we're working on. Starting at 0, this is t minutes. And the critical number, this one right here, we'll just throw it down on the diagram, 9.13. So this is how the first derivative test ought to go. And this would be a required step on both the quiz and the exam. And it's really tricky because WebAssign has no clue if you did this step or not, but it's an expectation for credit. So next thing you need to do is go here. Let me see if I can fit that a little bit better first. Didn't really give myself too much space to work with here. There we go. We have 2 regions. One is a finite length. The second region is infinitely long. And both of them, we're trying to determine the sign of B prime. So we'll throw B prime on both. Over here, a test value of 1 is probably the easiest thing to work with. And over here, test value of 10 minutes will be the next easier one. We're throwing all that right here, inside the first derivative. So in place of where the t's occur in 2 positions, when time is 1 minute, we have B prime at 1 minute becomes, well, this is e negative 0.1095 times 1, so I'll just leave it like that. Inside here, it's a 26.9 minus a 29, or 2.9 for 555 times 1, so we'll just drop the times 1. The first portion is positive, and it's always positive. But this is a 26 minus basically a 3, so the second factor is positive. We'll just say the whole thing is positive in this region. So greater than 0 goes here. And that means in this region, we just established that blood alcohol level is increasing in that case, which makes sense. At time 0, that's when the shot hits your system. Now blood alcohol content is rising. And right at 9.13, we better show that it transitions to decreasing, so the sign flips. This is more of a check at this point. If I get positive twice, you might suspect the exam question is wrong, but this one should work out. It might just be there's a mistake somewhere inside here. If you don't find the mistake, try not to erase everything. You still get partial credit. But if something goes wrong, just move to the conclusion. You might just have a small point loss right here. No big deal. But let's try it out again. B prime at 10 equals, first we throw 10 right here. That's just going to shift the decimal place 1 spot to the right. E negative 1.095. Copy in 26.9 next. Now we're multiplying by 10 right here, so now it's a negative 29.4555. And looking at the setup here, I wouldn't even put this in the calculator. Looking at, you have 26, or rather about 27 minus about 30. That's got to be negative. So put less than 0 there, which tells us it's decreasing. So now we've got the first derivative test pretty much all worked out. We just need to state our conclusion, and that's step 3. Any questions, folks, with the analysis here on the number line? Oh, I did forget one thing. Let me put here, forgot to put the negative sign on that. It's weird. I said decreasing, but neglected this one little portion. That wouldn't be a big deal if you neglected that. I would look over here on your work and know that you meant it. So negative here, positive here. That means we found a critical number C. And the derivative was positive for all x less than C. That's what's happening over here. The derivative is negative for all x bigger than C. That's what's happening over here. That means we're leading towards an absolute maximum. I would double check the instructions here because sometimes the conclusion you want to give is the value here. Other times the conclusion you have to give is the actual blood alcohol concentration level. So looking at the wording, it was asked at what time is blood alcohol maximized at its peak? That means this is the answer. We just need to state it. Let's say here at 9.13 minutes, and I'm looking at my units right here. That was definitely the wrong units. Nanograms per liter is we plug that inside the B function. Has units milligrams per liter. Sorry for that mistake right there starting out. That was time, so that should have been minutes. Units are meant to help us out. I wouldn't take off credit if you did put them on, but don't do as I did. If you put in the wrong unit, that could make something correct just look wrong. So at 9.13 minutes after consumption, blood alcohol level is maximized. This is a tricky kind of analysis because the function that we're working on might be a function that is about right for the average person in the population, but probably doesn't work on you. There's a load of variation from person to person to person on how well their liver is going to metabolize this kind of stuff. But on average, if you see someone take a really huge shot, you've got about 10 minutes to get out of there before they start acting a little bit differently. But any questions at all, folks, with the conclusion here? Okay, I would think of this as a pretty routine and typical exam 3 question. We can go right at the test. We don't have to worry too much about building a function. Analyzing its domain wasn't too bad. It makes sense. We should start right at 0. So if you can get through a question like this, you're on the great track. The exam question I'm going to write, you could use either the first derivative test or the second derivative test, but there will be a natural choice. There will be an easier one to take a look at and pick. If you go through all the notes on this section, there's a lot of advice on what makes the easiest test. It's just based off, if your second derivative is easy to calculate, that's probably the better test. But if it took you a lot of fighting, and we did fight with it, to just get to the first derivative, there's the work, you probably do want to use the first derivative test. So usually you choose the test after you get differentiating is good advice. Well, this is where the notes finally ends. Any last questions whatsoever, folks, before we now transition to 4.6? Okay, let's save this up. I must have already, oh, there it goes, it's saving. I like that we get like a 10, 15 second mental break while Microsoft Word tries to save all the digital ink on here. If we had like a 2-hour class, Microsoft Word wouldn't work at all. It'd probably just crash after you put enough stuff on there. So now we're finally in section 4.6, antiderivatives. It's a weird looking title, and it seems like we're going to be doing some crazy stuff. In fact, there's a revision right away. The function I put here should have had a minus x. So if you printed these out already, my apologies. Definitely put in a minus x. Not because it's required, it just makes part B flow a little bit better. So if we're dealing with antiderivatives, let's first read through the notation. The antiderivative I'm going to indicate as an uppercase function f. And I'll write it in blue in these notes just for the sake of color coding. It'll be called an antiderivative of the function lowercase f on some interval, provided when you differentiate your antiderivative, you get back the original function, and that holds for all x in that same interval. So that's what we mean by antiderivative. But because we have to check if we have an antiderivative by differentiation right here, it means This document is pretty much a good one to come back to. Differentiation formulas is back on the table. And these are the major ones that you'd want to have in mind when you're thinking about derivatives or antiderivatives. Our whole goal here is to reverse every formula that you see on these notes. Well, not so much these down below, that's more for completeness. More from here to here, we need to reverse all of those formulas that we've seen. To get started on that, first, let's do another careful check on what we mean by antiderivative. So provided on example 1 to get us started, I have a function f of x indicated in this way, so it's a power 5 polynomial. We want to know if it's an antiderivative for a degree 4 polynomial. On paper, that looks about right. If you differentiate this, the degree drops by 1, but you have to have equality perfectly right here. So the moment you think you have an antiderivative, here's what I would encourage you to do pretty much each and every single time you're in section 4.6, whether it's on WebAssign, whether you're doing a quiz problem or exam problem. Take your f of x, that's going to be the answer in the upcoming examples down below. Differentiate it, so slap it with a prime, and see what this comes out as. So this is now just a review of section 3.2. Power 5 comes down, multiplies the 2. We have 10 to the power of 1 less. It's now power 4. Down the line, the next one will be negative 6x. Derivative of 2x resolves as just a 2. And we're going for equality right here. But now when we compare, we're off by that 2. So instead of saying equality, we'll go is not equals to f of x. Now we need a conclusion. If you had not equals right here, that means the supplied function is not an antiderivative. Let's write down. This shows f is not an antiderivative. It's an antiderivative of something, but it's not an antiderivative of the original function f being mentioned right here. So that's how that one goes. And it's comforting to know that even though we haven't discussed on how to produce the antiderivative, that function, the check is really just doing chapter 3 again, checking your answers through differentiation. Well, we'll try it again on part B. First, any questions, folks, on our conclusion there? Okay, let's try it out again. This time we have a more complicated function, and a revision means I made a mistake on this one. I wanted this one to be an antiderivative, but it wasn't unless I put in that correction right there. So same question, we want to know if this function f of x is an antiderivative for that function. So all we have to do is start by differentiation. We also need to be careful because right here, that portion will be a product rule. So let's start off actually by doing the analysis, the setup for our product rule situation. The order I typically go is differentiate the first factor, x, multiply by natural log x, go plus, and take x, multiply by the derivative of natural log x. Then that takes care of the product rule portion. You still have to differentiate this part, negative x, but that would drop in as just a minus 1. So I did part of the derivative right here for this portion, and the rest of it is just the setup of the product rule. Okay, does that look right to folks so far to that stage? Okay, sounds like we're all happy with it. So let's proceed through the rest of the product rule. Derivative of x here turns into a 1, so 1 times natural log x plus x times derivative of natural log x right here. Hey, that's our review question for the day. Or yeah, that would be a review question on exam 3 so far. Any volunteers for the derivative right there of natural log x? Exactly. This one just takes your x, drops it down to the denominator, so 1 over x. The rest I'm just copying, minus 1. I still have to do some algebra on this thing. 1 times natural log x is the natural log of x. X multiplied by its reciprocal results in a 1. We're subtracting 1. And so this whole thing is now equal to natural log x. And I said that with the wrong inflection, just natural log x. That is our function f of x. I'll throw it in here for emphasis, because that now helps with our conclusion. It's all about this line right here. If you can make that happen, you have an antiderivative. So the connective glue is all those equalities. F prime connects to lowercase f of x. So here's our conclusion. We can say this shows f is an antiderivative of f. So we've done it, folks. We found an antiderivative, but you might have also noticed something a little bit jarring here. I didn't use the definite article, and most people would want to. You usually say you found the solution X or something along those lines. But I use the indefinite article right here to suggest, well, that's just one antiderivative. It turns out there are many, many more. For example, you could have done this. F of x equals x, natural log x, minus x, plus 7. That's also an antiderivative. So this is also an antiderivative. I want to put a more obvious border here. Let's go maybe this way. There we go. So that's just a related comment. The reason that's also an antiderivative is if you differentiate this function f of x, the derivative of this much right here is what turns into natural log x, resulting in f of x. So the fact that we add a plus 7 is irrelevant, because if you differentiate that plus 7, it's just gone. It doesn't even have to be a plus 7. It could be 71, something random. It could be essentially anything whatsoever. So any constant you put right here produces an antiderivative, and that means this constant 7 turns out to be a little bit more special. It's sometimes referred to as the constant of integration. That's what we'll start to call it in chapter 5 coming up next. But in this chapter, we're going to put in C right here, refer to it as an arbitrary constant, and it's playing the role of that 7. This way, we won't always say we found an antiderivative. If we put in an arbitrary constant, we'll say it is the antiderivative. The meaning it's a family of infinitely many different functions. You change the value of c here to maybe a 7, for example, or 71, or a 0. That would be this function right here when that value is 0. You have an antiderivative each and every time. And so we can now say here, since f prime of x equals, and we won't reinvent the wheel, we just differentiate all of this, that highlighted person, so we'll just put it in. That turned into natural log x. When you differentiate a constant, even if it's fully arbitrary, any real number whatsoever, derivative of a constant is always 0. This is equal to f of x. So since we got that equation to work out once again, we will now say in this context, this shows f is the, and that's a little bit weird to say because now it's the definite article, it is the antiderivative of f, lowercase f in this case. But the fact that we could throw a the right here, again, that's extra special, but it just means there is more than one function. There's infinitely many different ones. We're talking about the family of functions is correct. This one specifies every antiderivative all in one shot that could ever emerge of that function, natural log x. Well, that's kind of wild, but the whole discussion here was all about what does it look like when you really have an antiderivative? If you can verify that equation, then you're in good shape. Essentially, example one, the bigger takeaway is this is the check. This is how you check if you really have an antiderivative or not. Well, good news is it's all about differentiating on the check. The bad news is we now have to produce antiderivative formulas, but it'll be a good review of chapter 3 while we're working on it. Any other questions, folks, with our first example? Okay, well, now coming down to more serious examples. Example 2, think of example 2 as a good place to come back to if you want antiderivative formulas specifically. We're going to generate several of them down here on these notes. But I want to mention one of these problems is a lot nastier than all of the rest. It's so nasty, we made a big deal out of it, and we even did a derivation. So let's pull up those notes for motivation. Let's go to section 3.7. This is our work on derivatives of logarithmic functions. But there's one derivative here that's extra tricky. And I went right over it. That derivative is surprising. The fact that you can take the derivative of a natural log x, even with absolute values on it, that's the change on this problem, and get 1 over x, is so surprising we verified it. This is kind of a tough verification to see all at once. But keep that idea back in your mind because it's coming right back. In fact, it's so special, we'll put it on our notes here and drop it right there. That seems like a decent enough spot. Okay, with that out of the way, we'll have our reminder down there for one thing that's a little bit nasty about all these problems. But now let's get started. We want to find the antiderivative of each one of these functions. So now we're starting with the question, the antiderivative of f of x written this way, that's the answer. So we need to produce it now this time. And when we go to produce it, we will check it through differentiation. Now on the bottom right over here, I'm going to put down some stuff that I'll delete in a moment so the notes don't get too overwhelming. But for finding an antiderivative, here's the first thing you would actually want to do. That's a power function, so let's just state the rule for the power function derivative. If you take x to the power of n and differentiate it, the first thing that happens is n comes down. That's step 1. Let's call that step 1. The second thing that happens is that you multiply x. We don't always emphasize the multiplication, but this time we should if we're reversing a formula. That was step 2, the fact that you're multiplying x. And then the last and final step is we need a new exponent. The exponent goes down if you're differentiating. And now that's about to get extra confusing. It's n minus 1. That's step 3. And let's put down this emphasis. Goes down when differentiating. I did not fit that word in one line, so we'll use that hyphen trick. So now we're going to reverse every single thing about this process. Step 3 is step 1, and we reverse it. Step 2 is step 2. And step 1 is step 3. We reverse that as well. So here's how it goes. Antiderivative for f of x, if that was the original function, we start with writing down x. And this is now our new step 1. But instead of going down, it will go up. If you're finding an antiderivative of a power function, the power increases by 1. So now it's an n plus 1. The power has to go up by 1. Next thing you do is you don't multiply any longer. For reversing this rule, we divide the opposite thing. So we're going to take, let's write maybe this way. 1 over something is how this answer would typically be written. And what do we divide by? Well, not quite n any longer. we're dividing by that, n plus one. And there's in fact one additional thing we have to throw on here. Kind of scrolled through theorem one a little bit fast, or they completely scrolled through theorem one. It's a reminder that when we're finding an antiderivatives, we throw in the plus c right here to get the most general antiderivative. C is going to be the arbitrary constant. But for any question going forward where it says find the antiderivative, it's always assuming implicitly we're finding the most general one. So even when we get here, well, we reversed the power rule, that part's done. But this is just antiderivative. We want the family of all antiderivatives whatsoever. We do that by just slapping on an arbitrary constant. That's really easy to forget. It's a mistake I make a lot. If you made this mistake on a real exam question, you might lose a point. Only once. You won't lose a point on every single problem. You just get reminders. But if you notice I mess this up, definitely call it out. Just say, Mike, where's the constant? Or something along those lines. It's fantastically easy to forget that thing. But again, just for emphasis, when it says find the antiderivative, we require that portion. We're finding the family of all antiderivatives, is what it's really saying. Well, that is a lot of discussion for one antiderivative. What we've done is reversed this entire process. We'll leave it on the paper if we can fit it, but we might have to delete that so the notes don't get too busy. But think of this as an honest formula. And what you would do right after is check it out. So here is the check portion. In our check, all we're doing is differentiating, just much like example one. So if you're differentiating, you would go f prime of x. The first thing that happens when you do a derivative is n plus one comes down and multiplies right here. That's the purpose of having that n plus one in the denominator. It's n plus one over n plus one. The next thing you do is you come back right here. And because we're differentiating the check, the power goes down by one to just an n. This goes to zero, it's a constant. That simplifies to one. So it equals to x to the n, which is f of x. So if you can get back to f of x, your check is done. Well, any last questions, folks, with the analysis on this one? Okay, I did want to put one extra thing on here. Part A has a lot going on for it because it's a bona fide formula in its own right. Let's put down a warning on this thing. This is something that is really, really unusual with algebra and calculus coming together. There is one exception to this formula, exactly one, and it's a humongous exception. This will never work if n is -1. So we are assuming immediately n cannot be equal to -1, and this means if f of x equals 1 over x, that is x power 1 when you correct the exponent, this needs a different formula. So watch out for that exception. It could come into this form, f of x equals 1 over x, or it could just be written as x powered -1. But either way you look at it, the value of n is -1, and that doesn't fly right here. You still cannot divide by 0, even if it's a formula for differentiation. That causes so much havoc. That's why we're going to come back to it right here with the boxed out purple formula. But for the moment, let's keep on working through the problems, see what goes on with the next ones. That's really weird. That kind of worked. Let's see if it erases right. Okay. Erasing is actually kind of hard on these documents. There we go. Well, any last questions, folks, with how part A goes? Okay, so part A is a really important formula. Let's box it out just for even more emphasis. And now here's what an actual homework problem might look like if you're using part A, and it's a really fast concept question. We want the antiderivative of that function, 1 over x cubed. But think back, if you were differentiating that function, you wouldn't want to use it differentiate in that format either, because that's the quotient rule. But the moment you say y equals x to the power of -3, there's no need for a quotient rule. This is extremely vital for antiderivatives because there is no quotient rule as an antiderivative. You'd use something called integration by parts, but that goes beyond the Calculus 1 material. Some of these rules are very hard to reverse, it turns out. But if you write it this way, not so bad. We can just say f of x equals, we're finding the antiderivative. So even if we call it y, we're thinking of this as the lowercase f of x function, but color coding won't hurt. Now let's think back on what we have to do. The first thing that happens is from right up here, the power has to go up by 1. So that's the +1 part. So if the power is -3, it's now -2. The moment you have that new power, you go to this portion, you divide by whatever that exponent is. That's just your immediate next step. So this will be 1 over -2 if you like, or sometimes people write it this way, -1/2. Then from this portion, this is where I make a mistake often. So that's why I make a big deal out of it to kind of prevent myself from making a mistake. Anyone see what else we have to write down here next to finish it off? Exactly. We need our arbitrary constant of antiderivative of integration to get the most general antiderivative. So we'll throw in a plus c. And at this stage, the process is over. However, I highly encourage you to do this right away. Once you differentiate it, come back over here and do the check. The check is rapid, and this is familiar ground. And it's even more important. The more you do this check, the more connection you're going to make in your mind of this is the process of undoing a derivative, coming up with an antiderivative. And that's what chapter 5 is all about. This section is like survival for getting through chapter 5. So differentiate this right away, it would look like this. F prime of x equals, first thing that happens is -2 comes down and multiplies. So this is negative of -2 divided by 2. The power goes down by 1, so this is x power -3. Now the 2's cancel, the signs cancel, and if we get equals x power -3, which is equal to f of x, or this was a y function in our problem, then that's where we were happy. We matched up the given function after differentiating this. So that means it's a true antiderivative. Well, that's 2 down. We produced these ourselves. Any questions, folks, with our 2 results? Okay, part C is really interesting now. I'll leave this one up to the class. Any volunteers for antiderivative when f of x is e to the x? It definitely is confusing. Would you all agree? One thing that makes it confusing is we know that the derivative of e to the x is like the easiest derivative, right? So if we're doing antiderivatives, it feels like it should be harder. And it really kind of is because it's, again, maybe not a formula you would expect. If the derivative of e to the x is always e to the x, that means the antiderivative is itself e to the x. So if you were thinking that might be the right answer, good on you. You're on the right track with that. It's equal to e to the x. I just have to remember to throw on that constant. And the check almost looks silly at this point, but I still encourage you to do it because you're trying to build a connection between the new content of chapter 5, essentially, with what we were doing in chapter 3. So I'll always emphasize this when we're doing an antiderivative problem here. Let's do the check. F prime of x is going to be equal to, differentiate e to the x, it's itself, so we're on our way. That's a constant, so it's gone, and that's the result. But that e to the x is f of x. And so that's where the check succeeds. The whole problem is over right at that stage. That's kind of good news in a way, right? If you have a base e exponential function, Derivatives, every order derivative and every order antiderivative, well, it's going to involve the e to the x function, so that's kind of nice. But it's not so nice when you get to part D. Deserves its own new page, I'd say. Part D is tricky because, well, the derivative on that thing is tricky. If you need some motivation, you can go to section 3.7 and take a look at the, here we are, the differentiation formulas to help us out. We have derivatives of any exponential function, any logarithm. So over here, if it's 7 to the power x, let's start by writing down the formula. So the derivative with respect to x of an exponential function to base b at power x equals b to the power of x times the natural logarithm of b. So that's our formula right there. Now we're reversing everything about it, which means the multiplication right there is what's going to change for us. It'll turn into a division, kind of logical in a certain sense, but we won't know for sure unless we do the check. So first we'll just follow our intuition. If that's the given function f of x, then the antiderivative should be, much like what happened on this exponential function, we should pull up the 7x right away. So there it is. That should be part of the answer. But now, if we were differentiating, we would have multiplied by the natural logarithm of the base. If we're doing an antiderivative, we divide by the natural logarithm of the base, which is a 7. So my claim is that that's the answer right there. Oh, almost. We still need the arbitrary constant c. But before we are satisfied with it, it's a massively good hint to always check these answers. So here's the check. I'm doing this in pencil to say it's not an emphasized part of your answer. If you don't give me a check on a quiz problem or an exam question, I'll assume that you just did it mentally. I'm mostly looking right here. So the check is more for you, but again, when you're learning this stuff, it's now pretty much vital. So here's how it would go. The check is kind of confusing, to be completely honest. And what makes it confusing is that it just looks weird as a derivative you're about to take. That if we reformat it, it can be cleaned up. It's the same as 1 over natural log 7 multiplying 7 to the power of x. And this is a good point of view to take because now it reminds us we just have a constant right here multiplying a function. We can use the constant multiple rule now to help us differentiate. So now here's the earnest part of the check. That's an arbitrary, well, it's not arbitrary, it's 1 over natural log 7, but it's absolutely constant. Let's prove it to ourselves. 1 divided by natural logarithm of 7, it's about 0.5, just a little bit in excess. A bunch of digits there. These are almost guaranteed to be irrational numbers. So when you go to differentiate, the constant multiple rule says you just write in the constant to start. Then you differentiate this portion. The derivative of 7 to the power of x, we're following this format here, the formula in black, will be 7 to the power of x multiplied by the natural logarithm of 7. This constant falls out when we differentiate. But notice this algebraic miracle. The reason you want a natural log 7 in the denominator is because upon differentiating, you produce a natural log 7, which you must cancel out in order to get to the original function f of x. Look, we just did, that's f of x. So to complete the check, I'll just write equals f of x So we'll check there to say we are satisfied. That was the right check. That tells us then, yeah, that's the answer. So if this was 11 to the power of x, you'd get 11 power x divided by natural log 11 plus a constant. And that will work out each and every time. I find these ones really confusing because you might have noticed when we differentiate, this one's really common. These are like the exceptional questions, but they do come up. And when they come up, we have to remind ourselves these are the formulas in the background. And if it's an antiderivative, you just take that and it goes down into the denominator instead. Well, any questions, folks, with part D? that takes us finally to the weirdest exception of them all. Part E. There is exactly one function like this in all of reality where this rule totally breaks down. So if you have 1 over x cubed, that's okay. You can reverse the power rule. Any power here could be reversed. For example, if you have a function that goes like this, you can find the antiderivative of that. You just say uppercase f of x equals the power here goes up by 1. So now it's x to the power of 13. You now have to divide by 13 and throw a constant. So no problem whatsoever. And my claim is you can put almost anything there except one exception. -1 can never go into that position. That means you have a problem the moment you spot this function. So there is only one function like this. This is another one where it's worth our time to make a big deal out of it. It's super, super exceptional. I say there's only one like this, meaning this is the only one where the power rule reversed will totally fail. But still, we can find an antiderivative. It's pretty much that. When you differentiate when you differentiate the natural logarithm of x, or even the natural logarithm of the absolute value of x, you get that function right back. So that means the answer on this one is f of x equals, now if you said natural log x, you're partially right, but there's a downside with this function. The downside is if you plot that function, its domain is limited. And our hunt for an antiderivative is also a hunt for a function that has the maximal domain possible, so that our antiderivative will work in a maximal amount of situations. So the reason there's an absolute values there is because look what happens to the curve. Well, nothing happened. I got a warning. Hang on, let me try to fix this. Maximizing the screen was not an attempt to fix it. Natural log of the absolute value of x, there it goes. It just was picky with that one. We've duplicated the domain. The only exceptional value is still 0. You can't plug that in. But now negative values work, and that could be important to your problem, as well as positive values. So when we're looking for the most general antiderivative, it's this right here, and the constant. The reason all that goes down is because of this weird little formula right here, because it has to stay right there. I'll just box this out as the answer. And the fact that the power rule will fail if you try to put -1 in the formula. So that's our answer. And the easiest thing to forget about this is the fact you have a logarithm, the natural logarithm, but after that, it's really easy to miss you need absolute value around your x. So this is a major formula that is easy to miss. It could be really awful in WebAssign too, because you might have the natural log x with a parenthesis around your x, which means you're essentially correct. I'm not going to take an awful lot of points if you forget absolute value, but WebAssign will. They won't let us go past unless we know we're missing the absolute value on that one. So WebAssign can be a bit of a jerk on that problem as well. Well, we did, folks. These are the major things I'd want to show you before we take a look at the next grouping of problems. Any questions or comments at the moment? Okay, so all these are just really fast one-shot problems. But some problems do look like that in WebAssign. However, the majority of them look more like this. So here's where we're doing more earnest looking actual WebAssign problems. And when you're looking at all these, it's a concern when you see fractions or products or any of that kind of stuff. But keep in mind, here's how we're really doing these kinds of problems. It's going to be very similar to what we did in section, let's take a look here. I think this would be the better one to look at, product rule, quotient rule, because we're not doing these kinds of problems right here. These are extremely hard to undo. It's called integration by parts, and it's, I believe, chapter 7 in our book. Our problems all look like this. What you want to do is a spot of algebra first, and then here we differentiated. The antiderivative is just as fast. You try to find the antiderivative of this by doing the first factor, antiderivative of the second factor, and just put them together. It doesn't work. It falls right on its face. Just like how differentiating this function requires a product rule, we need to expand our function if it looks like this right here, or like this down below. So step one is really to just write out your f of x in a more simple form for finding an actual antiderivative. So let's expand out the numerators to start. It'll be x times 3x for 3x squared, x times -1, so negative x, 5 times 3x, so 15x, and 5 times -1 for a -5, all of which is divided by x. Now, I didn't combine the middle terms, so let's make that our next step. 3x squared plus 14x minus 5, all of which is divided by x. We really mean that. You can now go like this. Divide by x here, here, and here. So now we're actually dividing everything, so we can simplify even further. Going term by term, we'll call this one 3x. On the second term, x has vanished, so it's just a 14. And this one is super, super dangerous. So if you spotted the danger here, good on you. I wouldn't even leave the function in that format. It's sketchy in that format. If you write it like this, -5 times, let's get a good color here, 1 over x, then it reveals the problem immediately. A lot of this is just pattern recognition. So you want to write down your math in a way that reveals the pattern, and the fact that we got a 1 over x. Antiderivative of that part is going to be this, the natural log of x with an absolute value all around it. So you wouldn't even want to put this as an x power -1. Algebraically, it's correct, but we might lose the connection, the fact that it's 1 over x that's dangerous. So I usually leave it in that format to identify the pattern. Now at this stage, we're going to go term by term, finding antiderivatives as we go. Starting on this one. First thing that happens, well, let's copy in the 3. Now next thing, let's put in a little bit of extra space. Bring in this common base, which is x, and I'm hiding the power. No, I wasn't. That was to power 1, so it climbs up to power 2. It's now x squared. Once you have the new power, you divide by it, so I'll put in a 1/2 right here. You might have put in 3/2, and that's just as fine as way to go. But for now, for the next one, if it was a 14, well, there's really an x there. Just doesn't look like it. But this really is, you could think of it as 14x to the power of 0. So if you thought of it in those terms, sure, it's a little bit silly, but the new power on x here would be power 1. We just write x to the power of 1 like that. But even if you did put the power 1 right here, the next step is to divide by 1. But division by 1 doesn't affect your 14. So if you have a constant, usually all we do is we throw an x on it. Thinking in terms of differentiation, if you differentiate that, all that happens is x vanishes and you go back to the 14. So if you have multiple terms, sometimes this is what people do. They do a mental check every time they produce a new term by visualizing the derivative and double checking it comes out right. That's a fine strategy as well, if you like to check term by term. Now, next step, let me remove those emphases. We get a -5 here, but observing we produce a 1 over x in this location, this is the nasty one, it deserves purple or pink or whatever that is. We get the natural log of the absolute value of x. Then finally, add a constant. So we did it, folks. This is the first bigger, more fleshed out WebAssign kind of problem that we got through. It's not completely done. We still have to simplify our work here, but nothing major. We just would write this as 3/2 x squared plus 14x minus 5 times the natural log of absolute value of x plus a constant. Guess that wasn't really a big simplification. If something canceled, that would be a much bigger deal. I think that just looks weird to me, so I combine it as 3/2. Also keep in mind, there's expectation that once you get here, you have your answer. On a quiz and exam, you don't have to say or do anything further. But when you're learning this stuff, this is probably the most important part. The check is more important than your answer. I really stand by that statement because doing the check helps you really build the connection on coming up with the answer. So all we're doing is differentiating this stuff. F prime will be, first, when we differentiate, this 2 is going to come down and multiply. When it does that, it cancels the 2 in the denominator. So we just get 3 times x power 1, 1 less. The derivative of that will give us a plus 14. Derivative of this will get us minus 5 times 1 over x coming from this term. And double checking, well, it's not equal to that because we did a lot of algebra, right? Where I'm trying to get a check on is that. Once our algebra settled up and we are ready to find the antiderivative, that's where I'm trying to match it up. And yeah, we have 13x plus 14 minus 5 times 1 over x. So this is equal to f of x, which tells us we're happy. We have the right antiderivative and our work really is done. Well, that's 2 down or 1 down so far for example 1. Any questions, folks, on producing that answer? Okay, well, that was so fun. Let's just do it all over again. Part B just doesn't look super exciting, but we've dealt with these kinds of issues before when we're in chapter 3. Anything that involves a radical sign, whether it's a square root or a fifth root or worse, our major goal is to unwind that and actually exhibit the real exponent. So first step on this one is to write f of x equals, you have something divided by 2. So if it helps you with visualization, you could write this as 1/2 times x. If it's a square root, the power on it is 1/2 plus. This one looks like it's going to involve a little bit more exponent surgery. So let's do this one on the margin. This is a 2 divided by a fifth root of x squared. First thing I want to do with it is eliminate the fact that it's a fifth root. This turns into 2 divided by x to the power of 2. The thing to memorize is that the root is the denominator when you go to write it in exponential form. So if that was a 7th root, we'd be divided by 7. As a 5th root, we're dividing by 5. The next exponential trick is, this is no good in this format. It's like the y equals 1 over x cubed we did on example 1 part B. We need to take that base, throw it up into the numerator, which flips the sign on the exponent to -2/5. So it's that thing right there we want to find an antiderivative on. So back to this portion, we'll go plus 2. Oh, and I forgot my 2. Looking at the work over here, that 2 didn't survive, so let's just squeeze it in. It's not worth it doing this stuff on the margin if we don't copy it in, right? So 2 there. Finally, this turns into 2 x to the power of -2/5 plus e to the x. You'll notice the e to the x just gets mixed in with a lot of stuff just to see what we do. It's not meant to be a trick question, but for giving like 4 different terms, that's a common one to throw in. Then -9. So now this is much, much better to work on. You might have noticed now at this point, a lot of our antiderivatives are coming down to just reversing the power rule. So because of that importance, let's state it right here. If f of x equals x power n, then the antiderivative we want, uppercase f of x. Actually, let's do one better. We wrote that in blue. Let's keep that a common pattern in the notes. The antiderivative f of x will be this. Power of x is now n plus 1. We divide by n plus 1 and throw in a constant. So we're about to do that 3 different times. Here's the formula we're about to use. And now we're ready to get started on this thing in earnest. So if that's our function f, the antiderivative would go like this. First thing, let's copy in that 1/2 that's been indicated. Give it a little bit additional space. And this has to go up by 1. So that means we're not subtracting 2/2, we're adding 2/2 to it. The new power should then be 3/2. Well, the next step is, once we find that exponent that went here, we divide by that exponent. But we want to write our algebra as cleanly as possible. Division by a fraction is multiplication by its reciprocal, and that's always going to be the easiest thing to do. Otherwise, you'll have much more extra steps. It's harder to simplify. So just go 2/3, multiply by that reciprocal, and you're doing this in a much cleaner, faster, more stable way. Okay, that's 1 down. Then we go down the line, rinse and repeat with the second term. Plus 2 times, and give it a little bit of space. We take a look at the exponent, and any volunteers for what the new exponent should be? Not quite. That would be if we were differentiating. We would subtract 5/5. Exactly. We're adding 5/5 to this one because we're going the opposite direction. Again, this hurts my brain too, when there's directionalities now competing with each other. But think, always go up in powers for your antiderivative. And that's exactly right. Add 5/5, that's adding 1, going up by 1. You'll get 3/5. The critical step is now, when you see this, multiply by the reciprocal right away. So times 5/3. And now that's 2 down. I'll do this one. Antiderivative of e to the x is itself. So I stole the freebie, sorry about that. But how about this one? Anyone see the antiderivative of a simple -9? Or not quite. We have to throw in something on that thing to make it a right antiderivative. Yeah, good call. We just need the variable. So if you have a constant, throw in whatever the variable is. So -9x, and I did run out of space on this one. Let me see if I can move that over just a touch more. Oh, that doesn't look good. There we go, we'll make that work. Last thing is, don't forget the constant, plus c. So we just about have it. This one we do have to do some earnest simplification. These 2's will cancel out. We need to multiply the 2 by 5, but nothing major. A lot of copying, it looks like. So our answer is f of x equals 1/3 times x to the power 3/2 plus 10/3 x to the power 3/5 plus e to the x minus 9x plus a constant c. So we got it, folks. It took a lot of oxygen just to say it, but there it is. Then we're definitely still not done with it. That's the supposed answer, but we should check it out. Any questions, folks, to this stage first? Okay, sorry, I'm fighting with my Microsoft Word right here. There we go. Well, maybe. Weird. Usually don't want that button on. I'm having a hard time actually turning it off. How weird. Maybe that did it. Yeah, okay, we're all set. Sorry, just had a weird Microsoft Word issue. So next thing we have is, once we get here, we're performing a check. I'm not trying to get back to the original function. We've done some algebraic manipulations. We're trying to get back to this one, the moment we started the antiderivative process. So the check will go this way. We're differentiating our answer. So this process will say 1/3 comes in. Before you change the exponent, you multiply by it. So it's times 3/2. Now you decrease this by 1. So that means minus 2/2. That takes it down to 1/2. And over here, rinse and repeat. 10/3 will multiply the exponent, the old one, at 3/5. We have to subtract by 1, so minus 5/5. 3/5 minus 5/5 takes us to -2/5. And this is the nice one. Derivative of e to the x is itself. The derivative of a power 1 function is just the coefficient, -9. And this was constant, fully arbitrary, but it's constant, so nothing additional has to be put in. And we don't usually take a lot of steps on the check. You just do as much algebra and calculus to the point you're convinced you have the right thing. So I'm just going to do this much. Exhibit the cancellations. The 3/3 also cancels. 5 will go to that 10 twice. So it's just a glorified 2 right there. Now we check this function. We have, 1/2. I mean, it's a little ugly looking with the chicken scratches, but I see a half there times x power half, so that part's settled. 2, x to the power -2/5. Yep, that's there. Then we needed an e to the x of -9. So that is equal to lowercase f of x. And that means our check is complete. We truly do have the answer right at that stage. Well, we did it, folks. That's a few pretty challenging problems. Part C looks like really more of the same kind of stuff. I cannot find the antiderivative by doing the antiderivative here, here, and here, and just putting them together. And we shouldn't expect that, because if you differentiate this thing, finding the derivative of this portion, and this portion, and just putting them together, that also doesn't work. You need a 3-factor product rule to make this happen if you're differentiating. So just like in a lot of problems in section 3.2, we need to expand all of this out, put it in the right format, and then we'll be on the right track. That's going to be probably more than 3 minutes and some change. So we're at a good stopping point for the moment. Any questions at all, folks, for what we've done so far? Okay, well, some last parting thoughts before we do call it a night. This is pretty good material right here because, I mean, exam 3 really is all about more stuff about derivatives. Even these things, which are all about optimization, what do you do as a first step? You differentiate and set something equal to 0 and you solve. So we are reviewing it in a certain sense in section 4.3, or excuse me, 4.6. But 4.6 is not on the third exam. So just a reminder again, if you do have questions you'd like to discuss amongst any one of these sections as the start of Wednesday's class, we'll make that a student-directed informal review. And once we run out of questions, we'll just come back here and practice more antiderivatives. It's not meant to be a threat or anything. That's just the next natural thing we would do right after. Well, we'll stop right here and call it a night. Have a great night, folks. And on Wednesday, we'll make that informal review happen. And keep in mind, there's also, when you're looking at review problems and review questions, definitely take a look at these notes, orient yourself with it, and it'll help out quite a lot. Well, have a great day, folks. I'll see you all on a Wednesday.